What if everything we thought we knew about black holes was wrong? Picture the most extreme place in the universe, a point of no return where gravity is so intense, not even light can escape. This isn't just science fiction, it's the edge of a black hole's event horizon, a boundary that hides some of the deepest mysteries in physics. But here's where things get even stranger. According to our current understanding, black holes shouldn't just trap matter and energy, they should also destroy information, violating one of the most sacred principles of quantum mechanics. This is the quantum information paradox, a cosmic contradiction that threatens to upend our fundamental laws of reality. Now imagine this scenario playing out on an unimaginable scale. A star collapses, forming a black hole, and with it, every bit of information about that star's existence, every atom, every particle seems to vanish forever. But quantum mechanics insists that information can never truly be lost. So where does it go? This paradox has led physicists to propose something even more radical: black hole firewalls. These are theoretical walls of searing energy at the event horizon, burning up anything that crosses them. If they exist, they could mean that spacetime itself isn't smooth and continuous as predicted, but instead littered with violent boundaries that challenge our very notion of reality. This isn't just an academic debate, it's a battle for the soul of physics. On one side, quantum mechanics with its unbreakable rule that information must be preserved. On the other, general relativity, describing a universe where black holes erase information without a trace. Bridging these two theories is one of the greatest challenges in modern science, and the answers could redefine our understanding of the cosmos. In this video, we'll journey beyond the event horizon to explore this paradox, uncover the startling idea of firewalls, and discover why solving this puzzle might be the key to unlocking the next revolution in physics. The stakes couldn't be higher, because if black holes can break the rules, what else don't we know about the universe? Black holes are cosmic anomalies so powerful they bend the very fabric of reality. Imagine an object with gravity so overwhelming that nothing, not planets, not stars, not even light itself, can resist its pull once it crosses a certain threshold. This boundary is called the event horizon, the ultimate point of no return. Beyond it, the laws of physics as we know them begin to unravel. At the heart of a black hole lies the singularity, a point where matter is crushed into infinite density, warping spacetime beyond recognition. The first direct image of a black hole, captured in 2019, gave us a glimpse of this monstrous phenomenon. The glowing ring of light surrounding the dark shadow wasn't just a scientific triumph, it was a confirmation of predictions. The black hole's immense gravity bent light around it, creating a silhouette that matched theoretical models perfectly. But while we've observed their effects, black holes remain shrouded in mystery. They don't just consume matter, they erase the very information that defines it, challenging everything quantum mechanics tells us about the universe. What makes black holes truly bizarre is how they distort time and space. Picture dropping a clock into one. As it nears the event horizon, time would appear to slow down from an outside observer's perspective, eventually freezing completely. Meanwhile, the clock itself would experience something far more violent, stretched and shredded by tidal forces in a process called. Yet despite their destructive power, black holes aren't cosmic vacuum cleaners, endlessly sucking in everything around them. Their gravitational pull follows the same inverse square law as any other massive object. Get too close, and escape becomes impossible, but keep your distance and you're safe. This delicate balance between destruction and predictability makes black holes the ultimate paradox. They're both the simplest objects in the universe, defined only by mass, spin, and charge, and the most complex, hiding secrets that could rewrite physics. And now, with the quantum information paradox and the firewall hypothesis, we're forced to ask, are black holes the keys to a deeper theory that unites gravity and quantum mechanics, or are they cosmic glitches that expose flaws in our understanding? The journey to find out starts right at the edge of the event horizon. Theory of general relativity revolutionized our understanding of gravity, not as a force pulling objects together, but as the bending of spacetime itself. Picture the universe as a vast, stretchy fabric. When you place a heavy object like a star on this fabric, it creates a deep curve, a gravity well. Now imagine something so dense, so massive, that it punches a hole straight through the fabric. That's essentially what a black hole does. According to general relativity, black holes are regions where spacetime curves infinitely, creating a one-way exit from our universe. The mathematics behind this idea came from, who in 1916, just months after published his theory, found an exact solution to the equations of general relativity describing a perfectly spherical, non-rotating black hole. The solution introduced the concept of the event horizon, a boundary where gravity becomes so intense that escape velocity exceeds the speed of light. Beyond this point, time and space switch roles. Falling toward the singularity, time becomes as inevitable as forward motion is in our everyday world. One of general relativity's most mind-bending predictions is time dilation near a black hole. Imagine two astronauts, one stays far away while the other descends toward the event horizon. To the distant observer, the descending astronaut's clock ticks slower and slower, appearing to freeze completely at the horizon. But from the astronaut's perspective, time flows normally, even as tidal forces stretch and compress them into oblivion. This paradox isn't just theoretical. GPS satellites orbiting Earth must account for tiny relativistic time shifts to stay accurate. Near a black hole, the effect is catastrophic. What's striking about general relativity's description of black holes is their eerie simplicity. No matter how complex the star that formed them, black holes are defined by just three properties: mass, spin, and electric charge. This idea, called the no-hair theorem, suggests that all other details, chemical composition, magnetic fields, even the star's history, are erased when the black hole forms. To general relativity, black holes are smooth, featureless pits in spacetime, governed by elegant equations. Yet this very simplicity hides a coming storm. Quantum mechanics, the other pillar of modern physics, insists that information, the detailed state of every particle, can never be destroyed. So when general relativity claims black holes swallow information without a trace, it sets the stage for an epic clash between two theories that have never been reconciled. This masterpiece describes black holes as perfect cosmic vacuums, but as we'll see, quantum mechanics paints a far messier picture, one where the event horizon might not be so smooth after all. Quantum mechanics is the rulebook for the universe at its smallest scales, a world where the ordinary laws of physics break down and reality behaves in ways that seem almost magical. At the heart of this theory lies superposition, the mind-bending idea that particles can exist in multiple states at once until measured. Think of a spinning coin. While it's in the air, it's neither fully heads nor tails, but some strange blend of both. Only when it lands does it choose a definite state. Now imagine this happening with electrons, photons, even entire molecules. That's the quantum world, a place where uncertainty isn't a flaw in our knowledge, but a fundamental property of nature. Then there's entanglement, a phenomenon famously called spooky action at a distance. When two particles become entangled, their properties link in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. It's as if you had a pair of dice that always land on matching numbers, even if you roll them on opposite sides of the galaxy. This bizarre connection defies our classical intuition about space and time, yet experiments have confirmed it time and again. But perhaps the most sacred principle in quantum mechanics is unitarity, the idea that information about a system state is never truly lost. Every interaction, every collision, every transformation preserves the complete history of a particle's journey. You can scramble an egg, but in theory the universe remembers exactly how every atom was arranged before you cracked it. This principle is the backbone of quantum theory, ensuring that the past is never erased, only reshuffled. Now here's the problem. Black holes seem to break this rule. When matter falls into one, general relativity tells us it's crushed into oblivion at the singularity, taking all its quantum information with it. But quantum mechanics insists that information can't just vanish, it has to go somewhere. This contradiction isn't just a minor technicality, it's a full-blown crisis in physics. If black holes really do destroy information, then one of our most trusted theories is fundamentally wrong. But if they don't, then this elegant description of spacetime needs a radical update. The stakes couldn't be higher. Resolving this paradox isn't just about understanding black holes, it's about uncovering the hidden laws that govern reality itself. Some physicists believe the answer lies in the strange, fuzzy boundary of the event horizon, where quantum effects might scramble information without erasing it. Others argue for even wilder possibilities, like hidden dimensions or parallel universes. One thing's for certain. The solution, when we find it, won't just rewrite textbooks, it could redefine our place in the cosmos. The heart of the quantum information paradox beats with a terrifying question. If the universe never forgets, how can black holes make information disappear? Picture a library where every book is written in unbreakable code, preserving every word ever written. Now imagine tossing one of those books into a fire. Quantum mechanics says the information inside should still exist, just scrambled beyond recognition. But black holes, they don't just burn the book, they seem to erase its very existence. This dilemma exploded into focus when Stephen Hawking made a startling discovery in the 1970s. Black holes, he argued, aren't completely black. Due to quantum fluctuations near the event horizon, they slowly leak energy, a faint glow now called Hawking radiation. Over unimaginable eons, this drip of particles would cause the black hole to shrink and ultimately vanish. But here's the catch. Hawking's equations suggested the radiation carried no trace of the information swallowed by the black hole. It was like watching a supercomputer dissolve into random static, with no way to recover the files it once held. The implications sent shockwaves through physics. If Hawking was right, the universe had a cosmic backspace key, a way to permanently delete the most fundamental building blocks of reality, and other physicists reacted with something close to outrage. Quantum mechanics had survived every test for nearly a century, and now black holes threatened to unravel its core principle. The stage was set for what became known as the Black Hole War, a decades-long battle between titans of theoretical physics. Its counter-argument hinged on a radical idea. The information isn't lost, it's transformed. Imagine throwing a ceramic vase into a black hole. From the outside, you'd see it freeze at the event horizon, its image smeared into a two-dimensional hologram. But according to quantum theory, every detail about that vase, the arrangement of its atoms, the glaze's chemical composition, must somehow be encoded in the Hawking radiation. The challenge. Decoding that information would be like reconstructing a symphony from the echoes of a single note. What makes this debate so explosive isn't just the fate of hypothetical particles. If black holes truly destroy information, it would mean our universe has a fundamental flaw, a crack in the foundation of reality itself. But if they preserve it in some scrambled, holographic form, we might be on the verge of discovering physics' holy grail, a theory that stitches together quantum mechanics and gravity. The stakes of this war weren't just academic, they were existential. And as we'll see, the battlefield would soon shift to an even stranger frontier, the fiery walls of the event horizon. Hawking radiation is one of the strangest predictions in modern physics, a ghostly glow that shouldn't exist, yet could hold the key to solving the quantum information paradox. To understand how it works, we need to dive into the bizarre world of quantum fields. Even in empty space, these fields are never truly still. They constantly flicker with tiny fluctuations, particle-antiparticle pairs popping in and out of existence like bubbles in a fizzy drink. Most of these virtual particles annihilate each other instantly, vanishing without a trace. But near a black hole's event horizon, something extraordinary happens. Picture one of these particle pairs appearing right at the edge of the abyss. Gravity's grip is so strong here that one particle might get tugged inward while the other escapes, like two climbers on a rope where one slips over a cliff. The escaping particle becomes real, carrying away energy that, according to his famous equation, must come from somewhere. That somewhere is the black hole itself. Over eons, this slow leak siphons away the black hole's mass, causing it to shrink. This is Hawking radiation, a faint whisper of particles that, given enough time, could evaporate a black hole entirely. The irony is devastating. Hawking's math suggested these escaping particles were completely random, carrying no information about what fell into the black hole. That randomness is the problem. In quantum mechanics, information is never truly lost. It might be scrambled, but there's always a way, in theory, to reverse the process. It's like burning a book, but still being able to reconstruct every sentence from the ashes. Hawking radiation, however, seemed to burn the book and scatter the ashes into nothingness. This contradiction set off alarm bells. If black holes really could erase information, it would mean quantum mechanics, the framework behind everything from computers to chemistry, was fundamentally incomplete. Physicists faced an impossible choice: either rewrite quantum theory or accept that black holes violate its most sacred principle. But as we'll see, the solution might lie not in choosing one theory over the other, but in uncovering something deeper, a hidden layer of reality where gravity and quantum mechanics finally shake hands. The firewall hypothesis hits like a thunderbolt. What if the event horizon isn't a silent boundary, but a blazing inferno? Imagine approaching a black hole, expecting to cross smoothly into oblivion, only to collide with a searing wall of high-energy particles hotter than the core of a star. This isn't science fiction. It's a serious proposal by physicists trying to rescue quantum mechanics from the information paradox. The idea emerged from a simple but devastating realization. If black holes preserve information in their Hawking radiation, the cost might be turning their edges into cosmic kill zones. Here's the puzzle. To save quantum mechanics, rule that information can't be lost, physicists like Joe argued that the event horizon must become a firewall, a chaotic storm of particles where the smooth spacetime of relativity shatters. Think of it like a DVD player shredding a disk to preserve its data. The information isn't lost, but the disk itself is destroyed. In this case, the disk is anything crossing the horizon. The firewall ensures the information about what fell and gets imprinted on the escaping Hawking radiation, but at a horrific price. Anything touching the horizon would be vaporized instantly. This idea turns general relativity on its head. Its equations describe the event horizon as an uneventful place. A traveler wouldn't even notice crossing it. But firewalls suggest spacetime itself might have a kind of memory, storing information in a violent boundary layer. It's as if the universe, desperate to balance its quantum books, erects a firewall to scramble information without erasing it. The paradox: this solution creates new problems. If firewalls exist, then black holes aren't the smooth pits relativity predicts, but jagged, energetic frontiers where physics as we know it breaks down twice, first at the firewall, then again at the singularity. Critics of the firewall idea point to an even deeper mystery: who or what decides to turn on the firewall? Unlike a natural phenomenon, firewalls seem to require a cosmic accounting system that knows when and how to activate, an almost sentient enforcement of quantum rules. Others argue firewalls violate the equivalence principle, a cornerstone of relativity stating that free-falling observers shouldn't detect extreme forces unless they hit something solid. Imagine skydiving toward Earth, only to smash into an invisible brick wall miles above the ground. That's how radical firewalls would be for our understanding of gravity. Yet the debate has led to thrilling new insights. Some theories suggest firewalls might form only when black holes are old, after evaporating halfway. Others propose that entanglement, the quantum link between particles, could spread information without needing a firewall, like a secret code woven into spacetime itself. The mere existence of this hypothesis shows how desperate physicists are to reconcile quantum mechanics with gravity. Firewalls might not be the final answer, but they've ignited a revolution, forcing us to question whether the event horizon is a door, a wall, or something stranger still. A place where the universe fights to preserve its deepest secrets, no matter the cost. The AMPS paradox is like a cosmic chess game where every move to save quantum mechanics forces black holes into an impossible checkmate. Named after physicists and Sully, this thought experiment starts with a deceptively simple question. If information escapes a black hole through Hawking radiation, how does it get out without breaking the universe's deepest rules? Their answer leads to a terrifying conclusion. The event horizon might be hiding a lethal secret. Picture three characters in this drama: Alice, Bob, and an unlucky astronaut named Carol. Alice stays far from the black hole, observing Hawking radiation. Bob hovers near the event horizon while Carol takes the plunge. Here, where quantum mechanics throws a wrench into smooth spacetime. According to quantum theory, particles emitted as Hawking radiation must be entangled, linked in a mysterious, instantaneous connection, with two things at once: their partner particles inside the black hole and older radiation Alice detected earlier. This monogamy of entanglement means a particle can't be fully entangled with two different things simultaneously. It would be like a spy working for two rival agencies without either side knowing. The AMPS team realized this creates an impossible choice. If information about Carol's fate escapes via Hawking radiation, as quantum mechanics demands, then the fresh radiation near the horizon must be entangled with Alice's older radiation. But that breaks its entanglement with particles inside the black hole, violating quantum rules. The only way to preserve both sets of entanglements. A cataclysmic event at the horizon, a firewall that burns away the contradiction by annihilating anything trying to cross. This paradox turns the black hole's boundary into a quantum crime scene. Normally, entanglement spreads information like whispers in a crowd, subtle and interconnected. But AMPS shows that for information to escape a black hole intact, the horizon must become a violent scrambler, shredding entanglements in a blaze of energy. It's as if spacetime itself has when faced with an unsolvable quantum conflict, it opts for annihilation over inconsistency. Critics argue firewalls defy equivalence principle, which states free-falling observers shouldn't feel extreme forces until hitting the singularity. Supporters counter that quantum mechanics might demand new physics at horizons, a place where relativity and quantum laws collide so fiercely that ordinary spacetime dissolves. Either way, the AMPS paradox proves that black holes aren't just swallowing matter, they're forcing physicists to confront gaps in our understanding of reality itself. The firewall might be nature's brutal solution to an impossible equation, a warning that near the edge of a black hole, the universe plays by rules we're only beginning to glimpse. Quantum entanglement isn't just a strange quirk of the subatomic world. It's the glue holding the information paradox together, and the very thing threatening to tear it apart. Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one, and the other instantly responds, as if they're sharing a hidden language that bypasses space and time. Now, imagine this eerie connection playing out at the edge of a black hole, where Hawking radiation spits out entangled particles while their partners vanish into the abyss. This delicate quantum handshake is where the paradox reaches its breaking point. Hawking radiation relies on these entangled pairs. As one particle escapes, its twin falls inward, carrying negative energy that slowly drains the black hole's mass. But here's the catch: quantum mechanics demands that the escaping radiation must also carry information about what's inside the black hole, like a cosmic message in a bottle. The problem: that information was supposedly locked behind the event horizon, in the particles that fell in. For the outside universe to read the message, the escaped particles would need to somehow mirror their trapped partners, effectively copying their quantum states. And that's where physics slams on the brakes. The no-cloning theorem, a fundamental law of quantum mechanics, forbids perfect copying of quantum information. It's not just a technicality, it's what keeps the quantum world from descending into chaos. Think of it like trying to Xerox a fragile, three-dimensional snowflake. The original melts in the process, and the copy is just a flat, distorted shadow. Apply this to black holes and the paradox becomes clear. If Hawking radiation copies information from inside the black hole to the outside, it violates this sacred quantum rule. Yet if it doesn't, information is lost forever, which quantum mechanics also forbids. The universe, it seems, has painted itself into a corner. This dilemma exposes a terrifying rift between relativity and quantum theory. Equations treat the event horizon as a silent curtain, where nothing special happens, just a point of no return. But quantum mechanics, with its web of entanglements, suggests the horizon is more like a shredder violently scrambling information to preserve it. Some theories propose that the answer lies in the holographic principle, where all the information inside a black hole is somehow smeared across its surface like a cosmic barcode, encoded in tiny scale pixels. Others argue for wormholes, quantum tunnels that secretly connect the escaping particles to their trapped twins, preserving entanglement without cloning. The stakes couldn't be higher. If entanglement truly breaks down at the event horizon, it wouldn't just rewrite the rules for black holes. It would mean quantum mechanics itself has a fatal flaw. But if entanglement somehow survives, then spacetime might be far more flexible and far stranger than ever imagined. Either way, the solution will force us to rethink reality at its most fundamental level, revealing whether the universe is a seamless tapestry or a patchwork of contradictions barely holding together. This holographic principle turns our understanding of reality inside out, literally. Imagine taking everything inside a black hole, every atom, every particle collision, every shred of information, and compressing it onto a two-dimensional surface at its boundary, like stamping a detailed 3D sculpture onto a flat sheet of paper. This isn't just a metaphor. It's a radical proposal that the universe might fundamentally encode information this way, with the event horizon acting as a cosmic hard drive. The principle suggests that what we perceive as a three-dimensional world could, at its core, be a projection of data stored on a distant, two-dimensional surface, like a hologram where light tricks us into seeing depth where none physically exists. The roots of this idea stretch back to string theory, where physicists discovered a strange mathematical connection between theories describing gravity in higher dimensions and those describing particles in lower ones. It's as if the universe has a hidden redundancy, a way of writing the same story in two completely different languages. For black holes, this means the information swallowed by the singularity might never actually leave our universe. Instead, it's smeared across the event horizon in unimaginably tiny pixels, each no larger than the length, the smallest possible size in physics. But how could a flat surface hold all the complexity of a three-dimensional space? Think of a credit card hologram. Tilt it, and the image shifts as if it has depth, even though it's printed on a flat sticker. The holographic principle argues that spacetime might work the same way, with the event horizon encoding everything inside the black hole in a vast, scrambled quantum tapestry. This wouldn't just solve the information paradox. It would mean black holes don't destroy information at all. They just translate it into a form so alien we're still learning to read it. Yet this elegant solution comes with its own mysteries. If information lives on the horizon, what happens to the unlucky astronaut who falls in? From the outside, their data gets frozen onto the surface like a fossil in tar. But from their perspective, they plunge straight through. The holographic principle implies these two experiences, freezing and falling, must somehow both be true, forcing us to question whether spacetime is as objective as we thought. Could reality itself be a kind of illusion, a shadow play cast by deeper, hidden laws? The implications ripple far beyond black holes. If the holographic principle holds, our entire universe might be a projection from some distant, lower dimensional boundary, a cosmic illusion where depth, time, and even gravity emerge from a flatter, stranger reality. It's a dizzying thought, one that blurs the line between physics and philosophy. And while we don't yet have proof, this idea has already reshaped how we see the most fundamental question of all. What is reality, really? The answer might not lie in the stars, but in the invisible ink of quantum code written at the very edges of space and time. What if the key to unlocking the black hole information paradox lies not in the depths of a singularity, but painted across its surface like a cosmic fresco? This is the promise of AD-SCFT correspondence, a revelation so profound it bridges the chasm between gravity and quantum mechanics using the language of higher dimensions. Born from string theory in the late 1990s, this idea proposes an audacious trade. A black hole warping spacetime in 5 dimensions is mathematically equivalent to a swirling quantum field theory living on its 4-dimensional boundary. It's as if the universe has been running 2 completely different operating systems this whole time, and we've just discovered they're secretly the same program. At its heart, AD-SCFT suggests that the information swallowed by a black hole isn't destroyed, it's translated. Picture a futuristic scanner that could disassemble your body atom by atom, recording every detail onto a flat chip. The you that steps into the machine vanishes, but the information that made you persists in another form. Similarly, a star collapsing into a black hole might seem lost forever, but according to this duality, its quantum signature gets holographically imprinted onto the event horizon's surface. The equations show this boundary isn't just a passive membrane, it's a frenetic quantum system where particles dance in patterns mirroring the gravitational chaos inside. This correspondence turns the firewall debate on its head. If the black hole's interior is just a shadow cast by quantum interactions on its surface, there's no need for information to physically cross the horizon at all. Instead, what we perceive as 3-dimensional spacetime emerges from complex quantum entanglements in lower dimensions, like a 3D movie emerging from a flat screen. The violent paradoxes at the event horizon might simply be artifacts of our insistence on seeing space and time as fundamental, rather than emergent properties of something deeper. The implications ripple across physics. If AD-SCFT holds, it suggests our universe itself could be a hologram, a projection from some distant, flatter reality where gravity doesn't exist. While the math currently describes an idealized, negatively curved, anti-sitter space rather than our expanding cosmos, the principle hints that spacetime might not be the bedrock of reality, but a secondary effect. Every black hole could be a stone, teaching us to decode the quantum language underlying gravity itself. Yet mysteries remain. The duality works beautifully in abstract mathematical landscapes, but applying it to real black holes, let alone our universe, is like trying to play a vinyl record on a quantum turntable. The needle keeps skipping. Some theorists argue the correspondence reveals not a literal truth, but a profound clue about how information escapes black holes without violating quantum rules. Others see it as a stepping stone to an even grander theory, one where spacetime itself is built from entangled quantum bits. Either way, add-SCFT has given physicists something revolutionary, a dictionary for translating between two languages of reality, and perhaps a path to finally resolving the paradox that started it all. Its complementarity principle offers a daring escape from the firewall dilemma. What if the information paradox isn't a paradox at all, but a cosmic sleight of hand? Imagine standing outside a black hole, watching a book fall in. From your perspective, its pages would appear frozen at the event horizon, their information smeared into a quantum hologram on the surface. But for someone writing the book inward, it would plunge straight through, seemingly untouched. Its genius was realizing both perspectives could be true simultaneously, not because space-time is inconsistent, but because reality itself depends on who's looking. This idea mirrors one of quantum mechanics' oldest riddles, wave-particle duality. Light behaves as a wave when you measure its frequency, but as a particle when you detect its impact, not because light changes, but because measurement forces it to reveal one facet of its deeper, stranger nature. Complementarity applies the same logic to black holes. The event horizon isn't a physical barrier, it's a boundary of perspective. From outside, information never crosses, it's encoded in Hawking radiation. From inside, the horizon might as well not exist. Both realities coexist, just as an electron is both particle and wave until pinned down by observation. The implications rewrite the rules of locality and causality. Normally, we assume events happen in definite places and times. A cause here leads to an effect there. But complementarity suggests the universe has a kind of quantum split screen, where information can be in two places at once relative to different observers. It's as if spacetime itself is a flexible projection, adapting its story depending on where you're standing. This avoids firewalls by making the horizon's violence observer-dependent. A firewall exists only if you insist on reconciling both viewpoints into a single, objective reality. Critics argue this stretches quantum weirdness to cosmic scales. If a falling astronaut sees no firewall but an outside observer does, who's right? Answer: both, because physics isn't about universal truths but consistent experiences. Think of a rainbow, its position depends on where you stand, yet no one calls it an illusion. Similarly, black holes might force us to accept that spacetime's solidity is a local illusion, woven from entangled quantum threads that fray at horizons. The cost, our intuitive notions of causality unravel. If an effect inside the black hole can't be separated from its cause outside, then spacetime might be less a stage and more a tangled network of quantum connections. This could hint at a deeper reality where gravity emerges from quantum entanglement, a universe where black holes aren't cosmic dead ends, but mirrors reflecting the strange, dual nature of existence itself. What if the spooky link between entangled particles isn't just a quantum quirk, but a hidden tunnel through spacetime itself? This wild idea, known as ER equals EPR, dares to rewrite the rules of reality by suggesting that entanglement, the eerie connection called spooky action at a distance, might actually be a microscopic wormhole stitching particles together. Picture two electrons born from the same quantum event, forever linked no matter how far apart they drift. Instead of some invisible signal passing between them, they could be tethered by an invisible bridge, a tiny wormhole, or ER bridge, buried deep in the fabric of spacetime. The math behind this conjecture is as elegant as it is radical. Back in 1935, and proposed wormholes as theoretical shortcuts through space, and famously highlighted the paradox of entanglement in the same year. For decades, these ideas seemed unrelated, one a curiosity of general relativity, the other a quantum mystery. But in 2013, physicists made a staggering connection. What if the EPR paradox and ER bridges are two sides of the same cosmic coin? That entanglement doesn't just mirror the geometry of wormholes. It is the geometry, with every entangled pair secretly joined by a scale tunnel. If true, this would transform how we see black holes. Instead of information being lost forever at the singularity, it might traverse these hidden wormholes, emerging scrambled but intact in Hawking radiation. Imagine a black hole not as a cosmic shredder, but as a quantum, a machine that disassembles matter on one end and reassembles it on the other through a labyrinth of microscopic bridges. The event horizon wouldn't be a one-way street. It'd be a bustling hub of quantum traffic where information takes shortcuts through higher dimensions. Yet the implications go even deeper. ER equals EPR hints that spacetime itself might be built from entanglement. Think of the universe as a vast network of threads, each entangled connection adding a stitch to the fabric of reality. Wormholes would be the knots holding it all together, with black holes serving as cosmic looms, weaving new threads into the tapestry. This could explain why information can't be lost. It's not stored in space, but as space, with every bit encoded in the geometry of these hidden tunnels. Of course, the idea remains speculative. No one spotted a wormhole in the lab, and the scale math is fiendishly complex. But if ER equals EPR holds, it would mean that the universe has been playing a breathtaking trick on us all along, that the weirdest features of quantum mechanics and gravity aren't bugs, but features of a hidden architecture where entanglement and spacetime are one and the same. The next time you hear about particles communicating instantaneously across vast distances, remember, they might not be breaking the rules, they might just be taking a shortcut. String theory offers a radical reimagining of black holes, one where the terrifying singularity vanishes, replaced by a buzzing, tangled web of energy called a fuzzball. Picture the event horizon not as the edge of an empty void, but as the surface of an impossibly dense, frenetic knot of strings, the fundamental threads that string theory says make up all matter. These aren't the smooth, featureless pits of general relativity. They're seething masses where every bit of swallowed information gets woven into the fabric of the fuzzball itself, like a cosmic ball of yarn encoding its own history in every twist and loop. The fuzzball model solves two of the black hole's most vexing problems at once. First, it banishes the singularity, no more infinitely dense point where physics breaks down. Instead, the entire interior is filled with these vibrating strings, stretched to their limits but never collapsing into a mathematical absurdity. Second, it sidesteps the firewall paradox entirely. Since information isn't lost behind a horizon but stored in the fuzzball structure, there's no need for a violent scrambler to preserve quantum rules. It's as if the black hole digests information rather than incinerating it, keeping the universe's quantum ledger balanced. This idea flips classical black hole physics on its head. Instead of an empty spacetime warped by mass, fuzzballs propose that black holes are their own mass, a sprawling quantum mechanical entity where gravity and stringy physics merge. Imagine throwing a book into one. In the old model, it's crushed beyond recognition at the singularity. In the fuzzball model, the book's information gets shredded into strings, but those strings remain part of a larger, coherent whole. Over time, as the fuzzball emits Hawking radiation, that information could theoretically leak back out, scrambled but intact, like a message slowly unraveling from a knot. Yet for all its elegance, the fuzzball remains a hypothesis. String theory itself lacks experimental confirmation, and fuzzballs push its math into uncharted territory. Critics argue that without observable predictions, the model is more philosophy than physics. Supporters counter that it's the only framework so far that reconciles black holes with quantum mechanics without invoking apocalyptic firewalls or hidden dimensions. What makes fuzzballs thrilling isn't just their potential to solve the information paradox. It's how they redefine the nature of reality itself. If black holes are truly giant knots of strings, then spacetime might not be the smooth continuum described, but a foamy, dynamic fabric built from deeper, more vibrant threads. The universe's most destructive objects could also be its most creative, weaving chaos into order at scales we're only beginning to imagine. Loop quantum gravity offers a radically different vision of black holes, one where spacetime itself is woven from tiny, indivisible threads. Unlike string theory's vibrating filaments, this framework imagines space as a network of interconnected loops, a fabric so fine-grained that not even a singularity can pierce it. Picture the universe as a cosmic tapestry, with each stitch representing a quantum of space just a billionth of a trillionth the size of an atom. When matter collapses into a black hole, it doesn't vanish into an infinitely dense point. Instead, it hits a wall, not a firewall, but a quantum barrier where gravity's crushing force is countered by the discrete nature of spacetime itself. Carlo, one of loop quantum gravity's pioneers, suggests black holes might not be eternal prisons. As the collapsing matter reaches maximum compression, these quantum loops rebound in a cosmic bounce, like a ball hitting the floor and springing back up. In this scenario, the black hole's interior doesn't end in a singularity but transforms into a white hole, spewing out everything it once swallowed. Information isn't lost, it's delayed, trapped in a quantum limbo until the bounce flings it back into the universe. It's as if black holes are cosmic recycling centers, shredding matter into quantum confetti only to reassemble it eons later. This elegant sidestep avoids the need for firewalls entirely. If spacetime is fundamentally granular, the paradox of information loss melts away. No infinite densities, no mysterious walls of energy. The event horizon becomes a temporary checkpoint, not a point of no return. Calculations even hint that this process could leave detectable imprints in ancient light from the early universe, subtle echoes of black holes that bounced long before stars formed. Yet for all its ingenuity, loop quantum gravity faces the same hurdle as string theory: no smoking gun evidence. The scale loops are too small to observe directly, and white hole remnants remain theoretical phantoms. Critics argue that without experimental validation, the bounce hypothesis is more poetry than physics. But its power lies in reframing the debate, showing that the paradox might dissolve if we abandon the assumption that spacetime is smooth and continuous. What makes this approach so compelling isn't just its alternative to singularities, but its audacious reimagining of reality's fabric. If spacetime is truly woven from loops, then black holes aren't just cosmic oddities. They're stress tests for the universe's underlying structure. Every particle they swallow, every photon they trap, probes the limits of a quantum geometric universe we're only beginning to map. Whether this vision holds up or not, it proves one thing. The solution to the information paradox might not lie in choosing between quantum mechanics and gravity, but in rewriting the rules of spacetime itself. Black holes aren't just cosmic vacuum cleaners. They're also some of the universe's most efficient heat engines. This bizarre connection between gravity and thermodynamics started with a young physicist named Jacob, who made a startling claim in the 1970s. Black holes must have entropy. At first glance, this seems impossible. Entropy, a measure of disorder, typically applies to systems with moving parts, gases expanding, ice melting, eggs scrambling. How could a black hole, defined by its eerie simplicity, have any disorder at all? This insight came from a profound analogy. When matter falls into a black hole, it vanishes from our universe's observable inventory, just like energy disappearing into a furnace. But thermodynamics, second law, forbids entropy from ever decreasing, so argued that black holes must carry entropy proportional to their horizon's area, the only feature that grows when something is swallowed. Imagine throwing a deck of cards into one. From the outside, the cards' intricate order vanishes, but the black hole's surface area increases slightly, as if the universe keeps track of the lost information by stretching its boundary. This idea was initially met with skepticism, even by Stephen Hawking, who later discovered that black holes aren't just entropy sinks. They also emit radiation and have temperature. Hawking's math revealed an astonishing symmetry. Black holes obey the same thermodynamic laws as steam engines or stars. Their temperature depends inversely on their mass. Tiny black holes sizzle like hot coals, while colossal ones hover near absolute zero. This thermal behavior hinted at something deeper. If black holes radiate, they can evaporate, and if they have entropy, that entropy must encode information about what fell in. The holographic principle takes this further, suggesting the horizon's surface area isn't just a crude entropy counter, it's a literal hard drive. Every bit of information swallowed by the black hole gets smeared across its boundary in sized pixels like a cosmic QR code. But here's the catch. Thermodynamics tells us information is preserved, not how to read it. Retrieving data from Hawking radiation is like reconstructing a novel from ashes. The letters might still exist, but their order is scrambled beyond recognition. This leaves physics with a tantalizing puzzle. If black holes store information holographically, what mechanism unlocks it? Some theorists propose the horizon acts like a quantum computer, performing calculations so complex that decoding them would take longer than the universe's. Others suggest the information emerges only when the black hole fully evaporates, like a puzzle assembling itself in reverse. What's clear is that black hole thermodynamics bridges the gap between gravity and quantum mechanics, revealing a universe where even the darkest voids play by the rules, just in ways we're only beginning to decipher. The quest to unravel black hole mysteries isn't confined to chalkboards and supercomputers. Scientists are now recreating these cosmic enigmas in laboratories. Picture a tabletop experiment where ultra-cold atoms are manipulated to mimic an event horizon, creating artificial Hawking radiation in a controlled environment. These quantum simulators don't produce real black holes, but they allow physicists to test how information behaves under extreme conditions. One groundbreaking study used a carefully arranged chain of atoms to simulate particle pairs near a horizon, observing how quantum entanglement evolves, a crucial clue for understanding whether information can truly escape. When nature provides its own experiments, we watch with detectors spanning continents. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has captured spacetime ripples from colliding black holes over 1 billion light-years away. Each merger sends gravitational waves, undulations in the fabric of reality itself, that reveal astonishing details. The characteristic chirp of two black holes spiraling together matches predictions with uncanny precision, but subtle deviations in the signal could hint at new physics. Some theorists speculate that if firewalls exist, they might alter how horizons interact during collisions, leaving faint fingerprints in the gravitational echoes. Even more tantalizing are the black hole shadows captured by the Event Horizon Telescope. By linking radio telescopes across the globe, astronomers created an Earth-sized observatory capable of resolving the glowing plasma around supermassive black holes. The first image of M87's black hole in 2019 showed a crescent of light bending around the dark silhouette of its event horizon, a near-perfect match for general relativity's predictions. But future observations with enhanced resolution might detect anomalies, perhaps hints of quantum fuzziness or unexpected energy patterns that challenge our classical understanding. The James Space Telescope adds another dimension, studying how black holes influence their galactic neighborhoods. By analyzing the energetic jets and accretion disks swirling around these invisible giants, astronomers can indirectly probe horizon physics. Some models suggest that if information is preserved holographically, it might subtly influence how matter spirals inward, like cosmic breadcrumbs leading back to the original stellar material. While we haven't yet glimpsed firewalls or fuzzballs directly, each technological leap brings us closer. Quantum computers now simulate black hole entanglement with growing sophistication, while next-generation gravitational wave detectors like LISA will listen for collisions with unprecedented sensitivity. The universe may guard its secrets fiercely, but through ingenuity and perseverance, we're learning to read its deepest codes, one experiment, one observation, and one revolutionary idea at a time. Quantum computing could revolutionize our understanding of black holes by simulating behaviors too complex for classical computers to handle. Imagine a machine that doesn't just calculate probabilities, but actually mirrors the quantum chaos near an event horizon. Google's quantum supremacy experiment in 2019 showed how a quantum processor, like Sycamore, could solve a problem in minutes that would take traditional supercomputers, a tantalizing hint at the power these devices might wield. While that specific task was abstract, the underlying principle is profound. Quantum computers operate using qubits that can exist in multiple states simultaneously, eerily reminiscent of the superposition and entanglement defining black hole dynamics. One promising avenue is modeling Hawking radiation, the elusive glow that could hold the key to the information paradox. Classical computers struggle to simulate the quantum fluctuations near a horizon, where particle pairs pop in and out of existence faster than spacetime itself can react. But a quantum computer, with its ability to process entangled states natively, might recreate this dance in a controlled environment. Researchers are already designing algorithms to simulate how information could leak out via radiation, testing whether it remains scrambled or carries hidden signatures of what fell in. It's like trying to decode a scrambled radio transmission, but the quantum computer speaks the same language as the black hole. The potential doesn't stop there. Quantum simulations could test the firewall hypothesis by probing how entangled particles behave near a synthetic horizon. If a firewall exists, it would manifest as a sudden breakdown of entanglement, a glitch in the quantum code that might be detectable in lab-based analogs. Other teams are exploring how fuzzballs or holographic principles might play out in these simulations, watching to see if information spreads across a boundary as predicted or gets trapped in unexpected ways. Of course, this field is still in its infancy. Current quantum processors are noisy, error-prone, and limited to small-scale problems. Simulating even a toy black hole would require breakthroughs in error correction and qubit stability. But the trajectory is clear. As quantum hardware advances, so does our ability to stress-test theories that were once purely philosophical. The day may come when a quantum chip in a lab offers the first experimental evidence for how information escapes a black hole, not by peering into the cosmos, but by engineering a slice of its quantum reality right here on Earth. What makes this approach so thrilling is its potential to bridge the gap between abstract math and observable physics. Theorists can debate firewalls and fuzzballs endlessly, but a quantum simulation might finally provide data, a concrete signal in the noise. It's a reminder that the universe's deepest secrets aren't always hidden in distant galaxies. Sometimes they're waiting to be unlocked in the strange, shimmering world of qubits and quantum circuits, where the rules of gravity and quantum mechanics might finally shake hands. The quantum information paradox doesn't just challenge physics, it shakes the foundations of how we perceive reality itself. If black holes can force us to choose between smooth spacetime and quantum mechanics, unbreakable rules, what does that say about the nature of existence? Some physicists argue this isn't just a technical debate, it's a referendum on whether the universe is fundamentally real or if what we call reality is just an elaborate shadow play of information. puts it starkly. We're used to thinking of spacetime as the stage on which physics happens. But what if the stage is the thing that emerges from deeper, invisible processes? This idea flips centuries of intuition. From Newton to, we've imagined reality as a fixed backdrop, mountains, stars, even black holes existing independently of observation. But the firewall debate suggests spacetime might be more like a hologram, its apparent solidity an illusion woven from quantum entanglement. Imagine touching a wall and discovering your hand passes through because the brick was just a projection of data stored somewhere else. That's the radical possibility firewalls expose. The event horizon's violence might not be a flaw in our theories, but a glimpse behind the curtain, revealing reality's scaffolding. The implications ripple into philosophy. If complementarity is correct, if an astronaut sees no firewall while an outside observer does objective spacetime even exist? Or is reality observer-dependent, a cosmic version of the old thought experiment? If a tree falls in a black hole and no one measures it, does it make a singularity? This isn't just academic. It forces us to confront whether physics describes nature as it truly is or merely our limited tools for understanding it. Like fish trying to describe water, we might be missing the deeper medium in which spacetime swims. Yet some push back. Nobel laureate Roger argues that quantum gravity must preserve an objective reality, even if we don't yet grasp its geometry. Others propose that gravity itself isn't a fundamental force but an emergent effect, like temperature arising from atomic motion. In this view, black holes aren't destroying information. They're revealing that what we call information is the true bedrock of existence, with particles and forces as its surface ripples. Where does this leave us? Perhaps the most humbling lesson is that black holes aren't just cosmic puzzles, they're mirrors. They reflect back our deepest assumptions about reality and force us to question whether the universe operates by rules we can ever fully comprehend. As you watch this video, consider, are we uncovering the true nature of spacetime, or are we bumping against the limits of human cognition, like ants trying to map a cathedral? The answer, when it comes, might not just rewrite physics, it could redefine what it means to exist. The firewall hypothesis might solve the information paradox, but to many physicists, it feels like trading one cosmic catastrophe for another. It's equivalence principle, the idea that free-falling through space should feel indistinguishable from floating in zero gravity, lies at the heart of general relativity. It's what makes spacetime feel smooth and continuous. Firewalls shatter that elegance, replacing the event horizon with a chaotic inferno that would obliterate anything crossing it. Imagine skydiving toward Earth, only to smash into an invisible wall of flames miles above the ground. That's not just counterintuitive, it's a direct violation of relativity's core premise. Critics argue firewalls are a desperate patch to save quantum mechanics by wrecking gravity's most beautiful theory. The math might work, but the cost is staggering. If horizons are lethal, then black holes become cosmic anomalies with arbitrary boundaries where physics abruptly fails. It's like saying a river flows smoothly until it suddenly doesn't, with no rocks or rapids to explain the disruption. Why would nature build such a violent discontinuity into spacetime? Alternatives to firewalls aim for subtler solutions. One compelling idea comes from Stephen Hawking and his collaborators: soft hair. These aren't literal strands, but faint quantum imprints left on the horizon by infalling matter, like whispers etched into spacetime itself. Unlike firewalls, soft hair preserves equivalence principle. Information isn't burned away. It's gently woven into the horizon's fabric through nearly undetectable quantum fluctuations. Think of it as a black hole's way of taking notes in vanishingly tiny handwriting, rather than setting its diary on fire. Another critique focuses on the firewall's timing. If the horizon only becomes deadly when the black hole is old and half evaporated, what triggers the change? Quantum mechanics doesn't usually work with on-off switches. It's governed by probabilities, not sudden, dramatic phase shifts. This makes firewalls feel like a X for the information paradox. The backlash isn't just about aesthetics, it's about methodology. Good theories solve problems without creating bigger ones. Firewalls rescue quantum information but sacrifice relativity's most cherished principles. Soft hair and other alternatives try to thread the needle, suggesting that information escapes through quieter, less destructive means. Whether any of these ideas will hold up remains uncertain, but the debate itself reveals something profound. Black holes aren't just testing our theories, they're testing how we build them. When the universe forces you to choose between two pillars of physics, maybe the answer isn't to knock one down, but to dig deeper and find the foundation they both share. Stephen Hawking's final collaboration introduced an idea as delicate as it was profound. Black holes might wear a kind of quantum hair, not the wild, tangled mess of classical physics, but something far subtler. Picture the event horizon not as a blazing firewall, but as a surface etched with vanishingly faint imprints, like whispers written in vanishing ink. These aren't physical strands, but quantum particles so low energy they're called soft photons or gravitons with barely any strength to nudge an atom. Yet collectively, they could encode every bit of information swallowed by the black hole, stitching it into the fabric of spacetime itself. The elegance of soft hair lies in its minimalism. Instead of torching and fouling matter to preserve quantum rules, the horizon gently records its passage through these subtle disturbances. Think of it like dropping a pebble into a still pond. The ripples fade, but the water remembers the impact in nearly imperceptible vibrations. Similarly, as matter crosses the event horizon, it leaves behind soft particles that subtly alter the black hole's quantum state, imprinting data into Hawking radiation like a cosmic barcode. This way, information isn't lost or violently scrambled. It's quietly redistributed, preserved in the universe's fine print. Hawking and his collaborators saw this as a way to sidestep the firewall's brutality. If soft hair exists, there's no need for a fiery boundary to enforce quantum rules. The horizon remains smooth, its equivalence principle stays intact, and information escapes without drama. It's a solution that feels almost poetic, a black hole's memory stored not in some blazing inferno, but in the faintest tremors of reality. Yet the theory isn't without hurdles. The math behind soft hair remains incomplete, leaving gaps in how precisely information transfers to radiation. Some critics argue these quantum imprints might be too subtle to ever reconstruct, like trying to replay a symphony from the faint hum of a tuning fork. Others question whether soft hair can fully account for the sheer volume of data a black hole swallows. Can a horizon's whispers really capture the complexity of an entire star? What makes soft hair tantalizing, despite its unresolved edges, is how it bridges quantum mechanics and relativity without breaking either. It's a reminder that the universe's answers might not lie in grand cataclysms, but in the quietest corners of physics, where even the softest particles can hold the weight of cosmic secrets. Whether this theory ultimately holds or not, it proves that sometimes the most revolutionary ideas come not with a bang, but with a whisper. Gravitational waves might be carrying whispers from the edge of reality itself, subtle echoes that could reveal whether black holes are wrapped in firewalls, fuzzballs, or something even stranger. When two black holes collide, the ripples they send through spacetime, detected by observatories like LIGO, aren't just simple chirps. Some theorists argue these signals should contain faint reverberations, like a bell ringing with hidden overtones, if the event horizon isn't the smooth boundary predicted. These quantum echoes would arise if the horizon has structure, whether the searing chaos of a firewall, the tangled strings of a fuzzball, or some other quantum texture we haven't yet imagined. The hunt for these echoes began as a daring thought experiment. If black holes store information on their surfaces, as holographic theories suggest, then matter falling in might leave quantum fingerprints that subtly alter gravitational waves. Picture dropping a pebble into a pond. Normally, you'd see clean, circular ripples. But if the water's surface were covered in microscopic bumps, those ripples would scatter, creating secondary patterns. Similarly, if a black hole's horizon isn't perfectly smooth, the gravitational waves from a collision might carry secondary signals, delayed echoes of the main event. LIGO's unprecedented sensitivity made testing this possible. In 2017, a team led by physicists claimed to find tentative evidence of echoes in the aftermath of the first detected black hole merger. Their analysis suggested faint, repeating pulses in the data, like a cosmic stutter after the main gravitational wave bang. The scientific community erupted. Some hailed it as a potential breakthrough, while others criticized the statistical methods, arguing the signals could just be noise. Subsequent studies have swung back and forth, with some reanalyses supporting echoes and others dismissing them. The debate remains unresolved, but the mere possibility has injected urgency into the search. What makes echoes so compelling is their potential to bridge theory and observation. Firewalls, fuzzballs, and other exotic models all predict different echo signatures. A clean, repeating pattern might point to quantum fuzziness, while erratic spikes could hint at firewall-like turbulence. Even the absence of echoes would be meaningful. It would bolster smooth horizon and force theorists back to the drawing board. Future upgrades to LIGO and next-generation detectors like the telescope could settle the question, offering precision sharp enough to distinguish between quantum whispers and cosmic static. For now, echoes remain a tantalizing, maybe a shadow on the data that could vanish with better measurements or evolve into a revolution. But the hunt itself reveals how far we've come. Centuries ago, black holes were mere mathematical curiosities. Today, we're listening for their quantum murmurs, trying to decode what happens where spacetime itself frays. Whether echoes are real or not, they've already done something profound. They've turned the most abstract debates in physics into something we can test, measure, and maybe one day understand. Dark matter, the universe's silent enigma, could hold unexpected clues to the black hole information paradox. Though invisible and elusive, this mysterious substance makes up over 85% of all matter in the cosmos, weaving through galaxies and bending spacetime with its gravitational pull. But what happens when dark matter drifts too close to a black hole's event horizon? Could its unknown properties, particles that neither emit nor absorb light, somehow alter the way information behaves at the edge of oblivion? One tantalizing possibility is that dark matter interacts with black holes in ways standard physics hasn't yet accounted for. Imagine a type of dark particle that doesn't just pass through the horizon unnoticed but lingers near it, subtly tweaking the quantum fluctuations that produce Hawking radiation. If these particles carry their own unique quantum signatures, they might scramble or even amplify the radiation's information content, like a hidden hand shuffling cosmic dice. Some theorists speculate that certain dark matter candidates, like weakly interacting massive particles, WIMPs, or even more exotic axions, could create microscopic turbulence near the horizon, distorting the smooth spacetime predicted. Then there's the holographic principle. If black holes store information on their surfaces, could dark matter's gravitational influence warp that encoding? Picture a projector casting an image onto a curved screen. The deeper the curve, the more distorted the picture becomes. Dark matter's gravitational lensing might similarly twist the holographic data imprinted on a black hole's horizon, leaving faint but detectable anomalies in how information escapes. These wouldn't be firewalls, but something subtler, cosmic static in the signal, hinting at forces beyond the standard model. Of course, this remains speculative. Dark matter's true nature is still one of physics' greatest mysteries, and its potential role in black hole dynamics is a frontier barely explored. But if unifying quantum mechanics and gravity requires piecing together every cosmic clue, then ignoring dark matter would be like trying to solve a puzzle with half the pieces missing. The universe rarely leaves loose ends. Perhaps the key to the information paradox isn't just hidden in the voids of black holes, but woven into the invisible fabric of the cosmos itself. The search for answers might lie in the faintest signals. Future gravitational wave detectors, like the Laser Interferometer Space Antenna, could pick up distortions in black hole collisions caused by dark matter's unseen presence. Or next-generation telescopes, probing the hearts of galaxies, might spot anomalies in how black holes evaporate over eons. Even if dark matter's role proves minimal, the exercise is illuminating. It reminds us that black holes don't exist in isolation. They're part of a vast, interconnected cosmos where even the most elusive particles could hold the key to reality's deepest secrets. What if the information swallowed by black holes doesn't vanish? It just slips into another universe. This mind-bending idea ties the information paradox to multiverse theories, where black holes might not be cosmic dead ends but hidden doorways. Max, a physicist at MIT, famously categorized multiverses into 4 levels, each wilder than the last. At level 1, our universe is simply so vast that identical regions exist beyond our observable horizon. Level 2 introduces bubble universes, forever separate from ours due to eternal cosmic inflation. But it's level 3, the quantum multiverse, that sparks the most tantalizing possibilities. Here, every quantum decision spawns a new branch of reality, meaning somewhere in some alternate timeline, the information lost in a black hole might still exist, preserved in a parallel cosmos. Now take this a step further. If black holes truly are portals, their singularities might not be points of destruction, but bridges, wormholes, connecting our universe to another. Picture a library book tossed into a black hole here, only to reappear slightly scorched on a shelf in some distant dimension. The math even allows for it. Some solutions to general relativity describe black holes as tunnels rather than traps. Of course, this doesn't solve the paradox so much as outsource it. Information isn't destroyed, but retrieving it from another universe is as practical as mailing a letter to a fictional address. Level 4 multiverse cranks the strangeness higher, suggesting every mathematically possible universe exists somewhere. In this dizzying landscape, black holes could be cosmic routers, redirecting information into realities with entirely different physical laws. Imagine a black hole in our universe encoding data into Hawking radiation that, upon escaping, materializes as a burst of sound in a universe where air, not spacetime, is fundamental. It's a wild thought experiment, but it underscores how desperate physicists are to preserve information's sanctity, even if it means invoking unseen worlds. The catch, multiverse theories are, for now, more metaphysics than physics. Without observable evidence, they linger on the fringe, dazzling but untestable. Still, they offer something invaluable, a playground for the imagination. If black holes truly are laboratories for quantum gravity, perhaps their secrets aren't hidden in the depths of singularities, but in the echoes of countless other universes, whispering through the cracks in spacetime. Until we find a way to peek beyond the horizon, these ideas remain speculative. But in a cosmos this strange, who's to say what's impossible the next decade promises to revolutionize our understanding of black holes with tools so advanced? They'll make today's technology look like a child's telescope. The Event Horizon Telescope, which captured humanity's first black hole image in 2019, is undergoing upgrades that will sharpen its vision tenfold. Imagine switching from a blurry snapshot to a high-definition movie. This new resolution could reveal subtle distortions around event horizons, hinting at quantum fuzziness or even firewall-like turbulence. Meanwhile, the Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave detector set to launch in the 2030s, will listen for collisions between supermassive black holes with precision impossible on Earth. These cosmic crashes might carry echoes of quantum structure or hidden dimensions, encoded in spacetime ripples. On the quantum front, lab experiments are pushing boundaries too. Scientists are recreating black hole conditions using condensates, ultra-cold clouds of atoms where sound waves mimic event horizons. These analog black holes allow researchers to study Hawking radiation in controlled settings, testing whether information truly escapes or gets trapped. Meanwhile, quantum computers like IBM's Eagle processor are simulating entanglement networks near synthetic horizons, probing how information might scramble without being lost. It's like building a miniature universe in a chip, where every qubit holds a clue to the paradox. Kip, the Nobel laureate who helped pioneer gravitational wave detection, once said, "The most exciting breakthroughs begin not with answers, but with contradictions that refuse to go away." The information paradox is precisely that kind of catalyst, a cosmic riddle forcing us to invent tools that peel back layers of reality we didn't know existed. Whether the solution comes from a telescope, a quantum circuit, or an experiment not yet imagined, one thing is certain: the journey to solve it will rewrite physics itself. The next generation of discoveries won't just tell us what happens at the edge of a black hole. They'll reveal how spacetime, information, and quantum mechanics weave together into the deepest fabric of existence. One of the biggest misconceptions about black holes is that they're cosmic vacuum cleaners, endlessly sucking in everything around them. In reality, their gravity works just like any other massive object. It follows the inverse square law, meaning you'd have to get dangerously close to cross the point of no return. Picture Earth's gravity. We don't get pulled into the sun because we're orbiting at a safe distance. Black holes operate the same way. Stars and gas can orbit them peacefully for billions of years, just as planets orbit stars. The danger zone only begins at the event horizon, a boundary so precise you could theoretically skim its edge like a surfer riding a wave, if you had a ship that could withstand tidal forces. Another myth is that firewalls, those hypothetical walls of energy at the event horizon, are an established fact. The truth is far more nuanced. Firewalls remain a controversial hypothesis, born from desperate attempts to reconcile quantum mechanics with general relativity. They're not something we've observed or even definitively predicted. They're one possible solution to the information paradox, and many physicists argue they create more problems than they solve. Think of it like a detective story where every clue points to an impossible crime. Firewalls are one suspect, but the case is far from closed. Science thrives on this kind of uncertainty. It's not a weakness, but the engine of discovery. Then there's the idea that black holes are eternal prisons. Pop culture often portrays them as bottomless pits where matter vanishes forever, but Hawking radiation tells a different story. Given enough time, far longer than the current age of the universe, black holes evaporate, slowly leaking energy back into the cosmos. It's like an ice cube melting in reverse. The smaller it gets, the faster it disappears. This doesn't mean information is lost. It might be encoded in the radiation, scrambled beyond current recognition, but still fundamentally preserved. People also tend to conflate theories with guesses. In science, a theory isn't a hunch, it's a well-tested framework like evolution or plate tectonics. The theory of general relativity has survived every experimental challenge for over a century. Hypotheses like firewalls or fuzzballs are untested ideas that could become theories if evidence emerges. The difference is crucial. It's like weather forecasting versus climate science. One predicts rain next Tuesday, the other explains why storms form at all. The beauty of these misconceptions is that unraveling them reveals how science actually works. Black holes aren't just mysterious, they're mirrors reflecting our own misunderstandings. Every myth hides a deeper truth about gravity, quantum physics, or the nature of evidence itself. And that's what makes this journey so thrilling. The closer we look, the more we realize how much we have left to learn. His voice crackles with excitement when he talks about black holes. The universe is a relentless accountant, he says, leaning forward as if sharing a secret. It never loses information, it just finds creative places to stash it. For the holographic principle isn't just math, it's a cosmic safeguard ensuring every atom swallowed by a black hole leaves its fingerprint on the event horizon. Think of it like burning a library, he explains. The books are gone, but the heat radiating from the ashes, that's where the stories hide. His optimism is infectious, painting black holes not as monsters, but as puzzles waiting to be decoded. Sabine, on the other hand, isn't convinced. We're like kids arguing over what's inside a locked box, she counters, her tone laced with skepticism. What if the box is empty? What if our theories are just elegant ways of being wrong? For her, the firewall debate exposes physics, recurring sin, building castles in the air when the foundation might be rotten. Every time we hit a paradox, we invent 10 new dimensions or invisible strings to save the math. Maybe the answer's simpler. We're missing a law so fundamental, we haven't even imagined it yet. The contrast between these two giants couldn't be starker. Sees black holes as stones, their horizons etched with quantum code. Sees them as mirrors reflecting our hubris. Yet both share something deeper, a raw, almost rebellious curiosity. When describes entanglement as spacetime stitching, his hands move like a tailor pulling threads from thin air. Meanwhile, scowls at the metaphor. Stitching implies a fabric, she fires back. What if spacetime isn't the canvas, but the painting? Other voices weave through the debate. Carlo, architect of loop quantum gravity, offers a third path. Black holes aren't eternal. Their cosmic hiccups collapse, bounce, rebirth. His equations suggest singularities might be illusions, quantum loops snapping back like overstretched rubber bands. Meanwhile, Joe, before his passing, defended firewalls with the grim resolve of a soldier holding a bridge. Sometimes the universe is violent, he once said. Pretending otherwise is bad poetry. What makes these clashes so compelling isn't just the science, it's the humanity. Watch Sai's light up describing holograms or smirk when she dismantles an analogy. These aren't dispassionate calculators, they're storytellers wrestling with the grandest plot twist of all, a universe that might keep its secrets locked behind horizons no theory can yet breach. The real lesson, physics thrives not on consensus, but on the friction between brilliant minds refusing to surrender to the unknown. And perhaps that's the answer to the paradox. Not a tidy equation, but a reminder that the most profound truths often hide in the space between competing certainties. As puts it, the day we all agree is the day science dies. For once doesn't disagree, she just laughs. Fine, but when my simpler theory wins, I'll save you a seat at the lecture. If this journey through black holes and quantum paradoxes has left you hungry for more, there's a wealth of resources to fuel your curiosity, whether you're a casual explorer or an aspiring physicist. For those who love diving into books, The Black Hole War is a thrilling start. It reads like a scientific detective story, chronicling the decades-long battle over whether black holes destroy information. Wit and passion make complex ideas accessible, turning abstract debates into a page-turning narrative. If you're craving even deeper theory, Carlo's Reality is Not What It Seems offers a poetic yet rigorous introduction to loop quantum gravity, weaving together philosophy and cutting-edge physics. Prefer visuals? The documentary Black Hole Apocalypse, hosted by astrophysicist Levin on PBS, blends stunning animations with clear explanations of event horizons, singularities, and Hawking radiation. It's like a cosmic road trip to the edge of reality. For a more technical deep dive, the lecture series Quantum Gravity by physicist T on YouTube is a, though fair warning, his whiteboard scribbles might make your brain ache in the best way. Free online courses can also bridge the gap between pop science and theory. MIT's OpenCourseWare offers lectures on general relativity and quantum mechanics, while platforms like host beginner-friendly courses on astrophysics. The key is to start small, maybe with a documentary or popular science book, before tackling dense papers like the original AMPS Firewall paper or Hawking's seminal work on black hole radiation. But here's the crucial reminder. Even the experts are still wrestling with these questions. The papers you'll read might contradict each other. The lectures might leave you with more questions than answers. That's not a flaw, it's the heartbeat of science. When you stumble upon a YouTube talk where two Nobel laureates passionately disagree about firewalls, you're witnessing the messy, glorious process of discovery. So grab a book, queue up a lecture, or join an online physics forum. Just remember, every great theory began as a wild guess, and every cosmic mystery is an invitation to wonder. Imagine strapping into a spaceship and diving straight toward a black hole's event horizon. You've studied the equations, memorized the theories, but now the moment of truth arrives. As you cross the threshold, would you even notice the firewall? According to general relativity, the horizon should feel like nothing at all, a smooth passage into oblivion. But if firewalls are real, your last microseconds would be an explosion of unimaginable energy, your atoms shredded into quantum confetti. Which version feels true to you? The eerie silence of universe, or the violent last stand of quantum mechanics? This isn't just hypothetical, it's a litmus test for how you see reality's deepest rules. Now flip the perspective. Suppose you're observing from a safe distance, watching a friend make that fatal plunge. Through your telescope, their image freezes at the horizon, redshifting into nothingness as time slows to a crawl. Quantum mechanics insists their information must eventually leak back out via Hawking radiation. But is that truly your friend or just a scrambled facsimile? If their essence is preserved, where does it reside in those fading photons? The paradox forces us to confront a haunting question. Can information exist in two places at once, like a cosmic sleight of hand, or is the universe playing a darker game where nothing ever really returns? Here, where it gets even stranger. Some theories suggest both stories could be simultaneously true, that from your perspective, your friend's data burns onto the horizon's surface, while from their perspective, they sail obliviously into the void. It's as if reality itself fractures at the event horizon, with no objective truth to reconcile the two experiences. Does this feel like a satisfying answer or a philosophical cop-out? The tension between observer-dependent reality and universal laws cuts to the heart of modern physics. Now let's twist the experiment further. What if black holes aren't unique? Imagine a universe where every object, a book, a planet, even you, has a microscopic event horizon wrapping its surface, encoding its information holographically. Suddenly, the firewall debate isn't about distant cosmic monsters, but the nature of matter itself. Could the paradox be telling us that all of reality is a hologram, with black holes merely the most obvious cracks in the illusion? This is where we turn to you. The greatest breakthroughs often start with what-if scenarios scribbled on napkins or argued over coffee. So what's your take? Could firewalls be nature's brutal compromise, or is there a subtler answer hiding in the math? Maybe you're convinced by fuzzballs or suspect dark matter plays a role we haven't glimpsed yet. Drop your theories in the comments. No idea is too wild, because right now, even the experts are rewriting the rules. After all, the next big leap in physics might not come from a lab or a telescope, but from someone watching this video, daring to imagine the impossible. Black holes have long been more than just cosmic oddities. They're cultural icons, fueling our imaginations and shaping how we envision the far edges of reality. Take Christopher's Interstellar, where Gargantua, the film's supermassive black hole, became a character in its own right. With its swirling accretion disk and gravitational lensing bending starlight into a halo, it wasn't just eye candy. It was the most accurate depiction of a black hole ever put on screen, thanks to physicist Kip's equations. The film's portrayal of time dilation near the event horizon, where hours on a watery planet stretch into years for those waiting in orbit, wasn't just dramatic license. It was a visceral lesson in relativity, delivered with blockbuster spectacle. Yet for every Interstellar, there's a film like Event Horizon, where black holes morph into portals to literal hell. The movie's premise, a spaceship crew stumbling upon a vessel that's been to a dimension of pure chaos, throws physics out the airlock in favor of cosmic horror. While real black holes don't lead to Lovecraftian nightmares, the film's creative liberties reveal something profound. Black holes terrify us because they represent the ultimate unknown. They're cosmic tests, reflecting our deepest fears about what lies beyond the limits of human understanding. Even wildly inaccurate portrayals serve a purpose. Disney's The Black Hole in 1979 imagined a crew finding a manned station hovering near a singularity, complete with a robot army and a mad scientist. The science was laughable. No one's building a condo near an event horizon. But the film's haunting question, what happens inside a black hole, echoed the very puzzles physicists were wrestling with. It's no coincidence that Hawking radiation was discovered just a few years prior. Pop culture's obsession mirrored science's frontier. Then there's Trek's take, wormholes as galactic shortcuts, black holes as narrative traps. Star Trek, Discovery even wove in the mycelial network, a fungal-inspired subspace that bends spacetime. It's pure fantasy, but it captures a kernel of truth. Black holes challenge our notions of distance and connection. In reality, traversable wormholes remain hypothetical, but the show's technobabble isn't far from theories like ER equals EPR, where entanglement might create quantum tunnels through spacetime. The irony, these creative leaps often loop back into real science. Interstellar's black hole visualization led to genuine research papers on gravitational lensing. Contact's wormhole sequence, though fictional, sparked public fascination with bridges. Even Doctor Who's time-warping time vortex owes a debt to Hawking's work on closed curves. Sci-fi doesn't just borrow from physics, it gives back, inspiring new generations to ask, what if? Perhaps the most enduring legacy of black holes in culture is their role as metaphors. They're the ultimate plot device, unknowable, inevitable, bending narratives as surely as they bend light. From Andromeda Strain's microbial alien to Dead Space's marker signals, black holes and their fictional cousins represent the limits of human control. They remind us that some forces can't be conquered, only survived, or at least pondered from a safe distance. This dance between fact and fiction isn't just harmless fun. It's a feedback loop driving curiosity. When The Martian made orbital mechanics thrilling, or Arrival turned linguistic relativity into a plot twist, they proved something vital. Even flawed science storytelling can ignite the spark that leads to real discovery. After all, today's sci-fi dreamers are tomorrow's graduate students. And the next breakthrough might begin with a kid watching a black hole on screen and wondering, how close did they get to the truth?